Hi everyone. I hope, like I said, I hope you're having a great time at Functional Scala 2024. And this is my presentation on making Scala or platform-dependent types work in Scala. So, about me, real quick, I'm a solutions architect at Ingenico. I was born in the US in Oklahoma, but now I've moved to France since over 10 years ago now, and I live in Normandy. And I have a wife of 3 years and a little baby girl. And I'm interested in writing software for the Linux ecosystem using Scala, specifically more desktop user style programs than server style programs. And I haven't made a lot of headway on this because Scala is not easy to use with or not easy to mix with the Linux ecosystem. So the problems particularly is that the ecosystem in the Linux community is heavily focused on C, Python, and C++, and Scala usually lives on the JVM, making it subject to the JVM's walled garden. There's a number of libraries on the JVM to do interop with C, but they tend to clash with core JVM tenants such as write once, run anywhere, and the libraries for interop frequently require non-JVM code, reflection, or require writing Java. JNI, for example, requires writing C and Java code just to create a binding to a C library. Um, with this in mind, I started working on a library called Slink a number of years back, and it is using a new technology that was finalized in JVM 22 called java.lang.foreign. And the point of this library is to try to make a library that works extremely well with Scala and is also making usage of Scala's type system and features to improve safety when dealing with C. An example of using Scala's type system to improve C interop would be using capture checking to control memory management and make sure that pointers don't get passed into an area where their lifetime is no longer under control. Another option, though, is making sure that C code is checked by the Scala compiler and doing so with a write once, run anywhere style language like Scala is. So, what is exactly something that has been blocking me on Slink for a long time is these platform dependent types. I tried a naive implementation in Slink, but found rather quickly that my implementation was not type safe and the compiler wasn't helping me. So the problem with these platform dependent types is that they change shape and size based on the platform you're running on. As an example, and they're ubiquitous in C. So as an example, the long type in C is one of the basic primitives and it's platform dependent. And on a modern x64 processor, if you're running on Windows, that long type has a maximum size of 32 bits, which means it can store a number of around 4 billion in size. And on Linux and Mac, it's 64 bits, which is significantly larger. So if you want to use a long from C, you have to know what you're running on, even on modern day hardware. And so this is part of the reason platform dependent types has been such a problem for me is that they're everywhere and they just uh, they change shape without any kind of help from C to figure out what shape it currently is in. So an example of how deeply rooted this problem is JNA's implementation of C-long. They call it native long. And you can see from this code here that they have a constructor that takes a long. And there's no checking if this is on the right platform or not. So I can only imagine that this native long, if instantiated with a long on Windows, for example, would be truncated if it's too large. And that's the best case for the data loss. Another problem we have with the current state of platform dependent types is that unpacking them is even extremely difficult. Here we have an example unpacking function that would take a platform dependent type, and the only type we could return with the current setup is object. We don't have any information about what the type actually is on that platform. We would have to know what platform we're running on and do a bunch of casting just to have the right type come out of the system. So this is obviously error prone, and we'd like the Scala compiler, if possible, to help us out with that. Finally, in Slink, I would like to be able to have something like if-def sections. So here we have an example of some C code that's using if-def to create platform-dependent code depending on the system we're running on. So if we're running on Mac, this code would be the one that's compiled as opposed to the other pieces of code. This is very helpful for C developers who are trying to write platform independent code. And it would be nice to have something like this in Scala, but we can't have exactly the same thing because in C they can do something like this because they just skip compiling the code that isn't for their current platform, and they also compile for every platform. And we want to compile for one platform, and that's problematic when we have to have types that work for all platforms. So my research or my efforts have been to try to figure out a way to make Scala aware of all the types that can be and help the user in constructing these platform-dependent types. And so what I want from PDTs in Slink is that they're performant, that they have improved write once, run anywhere compatibility compared to the current state of the art, and platform-dependent code can be written, but it's all type checked, even when you're not compiling on that specific platform. And in order to do that, we need compile time knowable platform mapping data so that the compiler can know what platform you're running on and what mappings match or what mappings apply for that platform. And we also need helper methods for the platform dependent types, such as generic and specific instantiation. Generic here being that we don't have to have specific knowledge of what platform we're running on in order to do instantiation, and specific instantiation being the case where we have strong knowledge of the platform we're running on, and the instantiation is easier or more powerful because of it. Likewise, we want generic and specific unwrapping, generic math, and also the ability to write inline platform dependent code. And I would like all of this to be checked by the compiler and type safe. So to start with that, we need to deal with the platform mapping data. For that, we need to define a type that I'm calling target after the concept of target triplets that happen in cross-compiled code. These types need to be a sum. This target type needs to be a sum type of singletons. And so every leaf node in the hierarchy needs to be a singleton. And we can't use enum for this case because enums have a tendency to widen to the base type very eagerly, and I observed this in my testing. So the leaf types in an enum all too frequently resolve back to the base type target, and we want a specific target information if we can get that. Finally, we need to not use something like objects or case objects because we want to control how people can access the instances of the singletons as opposed to control this type itself. So in order to do that, we define target like this. It's a sealed trait, of course. Inside of its companion object, we define sealed classes, which represent the types of the singleton types, Linux x64, Win x64, and Mac x64, and we can add more later on when we support more platforms. And then finally, we have private values that encapsulate the instances of the singleton types. Finally, the user is given access to the target through this method, which does the platform detection and gives back the specific singleton type matching the platform currently being run. This way, the user has easy access to the types in order to reason about them, but no access to the singletons without going through us. And they can't spoof a wrong platform type, or it becomes harder. They have to use reflection and other trickery. So in order to encode the mapping for these targets, now we are going to move to match types. Match types were added in Scala 3, and they provide a way to perform type calculations that don't rely on abuse of implicits, generics, and type inference that we would have to use back in Scala 2. So they're very nice, they're very powerful. They can't be used in every situation, but in this case, they're rather easy to comprehend and use. So for mapping for C's long type, you would write a type like this, where you write a type M that takes a type T, which is a subtype of target, and we match on that T to see if it's either Linux x64 or Mac x64, and if it's one of those, the type backing the platform dependent type is a long. Otherwise, the type backing the platform dependent type isn't it. Using this type mapping, we know what we need and we know what we need to fill in the platform dependent type. And if we have information on the platform, we can do instantiation. Finally, we need a way to store these platform dependent type datas. And for that, I use opaque types. This is particularly helpful in my case because these opaque types have no runtime implementation other than their backing. So for example, if you define this opaque type logarithm, it erases at runtime into a double as opposed to being a unique type logarithm. And because of that property, they can be passed into java-lang.form without any kind of translation work or anything like that. They're ready to use just right when they're there. Currently, this implementation requires boxing for primitives, but hopefully with future JVM versions and Valhalla, we won't have to deal with that anymore, and we'll get even better performance. And so here I have an example of how you would define the PDT type. This PDT type is going to act like a super type for all of the PDTs, and it's backed by matchable at runtime. So, which is basically object in Java. And we have a method to create a PDT using get, and a method to extract data from a PDT called unwrap. Both of these methods are only available for use within a context where PDT is equal to the p-type passed in, which is going to be our subtypes of PDT. This way, when you're defining a PDT, you can use these methods, but you can't use them anywhere else in your code. So as an example of how you would define a PDT using all of these three techniques, here's a simple implementation of CLong. It's an opaque type that is a subtype of PDT and backed by PDT at runtime. We have the type mapping M here, where on Linux and Mac it's resolved to a long, otherwise it resolves to an int. And finally, we have the constructor here that uses pdt.get, and it's able to work here because the type CLong is equivalent to the type PDT within this file. Otherwise, elsewhere, you could not use this pdt.get method because of the requirement of having the equality between this type and this type. And so with the simple implementation, we can start to see things start to bear fruit. Here, I have two scopes. In one, I give a Win x64 context, although I'm not really giving it because I'm just using question mark as the instance. And inside of this scope, the apply method on CLong will not accept a long literal as input. It gives a compiler error for X, but it will accept an int for input. Inside of the second scope, where we've set into the context Linux x64, both of these lines compile because Linux CLong is understood to be long on Linux. So since we have specific information about the platform in these two scopes, we're able to do work with the apply method. The problem with defining like this, though, is that one of the goals of this work is to define a way that people can use my library and also define their own PDTs, and people using their own PDT. These user-defined PDTs can reason about how to use them relatively easy. So we need to create standardized behavior, specifically with regards to instantiation. And to do that, we define a type class named mapping. This mapping type class will bind mapping information, the mapping match type to the PDT type, act as an official way of stating that this type here is actually a PDT, and it provides instantiation and extraction methods for these types. And finally, it simplifies the definition of PDTs for everyone. So the way that type class is defined is looking like this, and we have the instantiation method apply. We have an extraction method unwrap, and it's rather easy to define these two methods using the methods we defined on PDT earlier. The problem is right now that these methods are both specific. You can see that they're specific by they take a type T that's a subtype of target and take that target in context so that it can have knowledge about the platform. But we want to provide methods of instantiation and extraction that don't require specific knowledge of the platform. And the first one of those that we can do is, I'm going to call it unspecific. So in order to add unspecific to this mapping type class, we have to define a few new things. First of all, the unspecific method will take as input a sum of all the valid types that can back a PDT, or the C-long PDT in specific. So in this case, C-long can be int or long in our supported targets, which we define here, Linux x64, Win x64, and Mac x64. So since it can be either an int or a long, the unspecific sum mapping will go through all those values, union them all together, and result in U being equivalent to int or long for C-long. On other types, the definition of unspecific would change based on this match type calculation, but it's got one single definition here. And also to do this definition, we have to add inline to the derivation method for mapping. And the question is, why do we have to do that for unspecific here? How do we implement this unspecific? Well, implementing unspecific ends up looking like this, and this is a nasty pattern that happens with these generic methods throughout my experiments, is that we always have to do this inspection of the target in order to find out what exactly we're running on, and then use the methods available to do instantiation to get a safe instantiation. And so the problem with this pattern is you have to, anytime you're doing one of these generic methods for these PDTs, you have to do this pattern matching on the target. And if the number of targets grows, and it will in the future, everywhere you define this has to grow with it. And so it's a recipe for a massively expanding code base, and also for the matches to get out of sync and stuff. So again, we're trying to make this as easy as possible for people to implement on their own. So how do we generalize this pattern? How do we make it not have to be defined anywhere? Well, another Scala 3 feature comes to help here, and that's polymorphic context functions. Here I've got a function that matches basically what we're doing. We were taking a type T, determining what its actual type was, the leaf type, then summoning a class tag for it, and then doing the application, all right? And that process, that type ends up resolving to something like this as a polymorphic context function type. So for all T, which is a subtype of target, and for in the case that there's an instance of target with type T in context, and for a given class tag MT, where M is the mapping and T is the target, we can produce an option P. We can expand this generalized type in order to produce a helper function on target that allows to summon class tags for the appropriate target you're running on, and leaves all of the code that has to match on that target all embedded inside of target. This inline will inline the code when you call it. But it's all of the code that's handling all these match cases are all embedded in the target class instead of being written everywhere. And likewise, since we are able to split this out and have the code that actually does the work separated out elsewhere, then we can use this reveal method to generate this match inside of type classes that need it, and summon the appropriate type classes to power what we need, and have all that code located in one place in the type class and derived specifically for the PDT it's working on without much user interaction. In the case of unspecific, since only one method in that mapping and that type class is using this pattern, we just call reveal inside of it, and it will generate the case classes and matching that was listed before. But this code will never change. Even if you change the supported targets or the number of targets available, this code will just generate what needs to be generated, and that's the single implementation you need for unspecific rather than changing it every time the number of targets or the supported targets change. Combining all this, we're now able to define generic type classes like this PDT numeric, which is like the numeric type but for PDTs. And this type exists separately because it takes a target as a context input and produces a P. So as long as there's a target in scope, you can do generic math on those PDTs that have this defined. And likewise, we can define a type class called integral mapping with stronger capabilities. It has two specific or generic instantiation methods from minima and to maxima, and these are defined for integral platform dependent types because we're able to reason about them a little more. In the case of long, we know that all types, no matter how its size changes, we always know that it's going to be an integral type. Since we know that, we can make certain assumptions about what is a safe input to it and what isn't. One of these assumptions powers from minima. From minima goes through the mapping you've provided for the PDT, looks at all the integral types that are in that mapping and resolves to the smallest integral type that's in that mapping. So for C-long, it can be instantiated with int on Windows and long on Linux and Mac, and int is the smallest. So since we know that for all platforms, at least an int is, we have at least an int worth of storage, we can write this from minima to take an int. And that's always a safe instantiation operation. And so that from minima is a safe generic instantiation that doesn't require an option. And because of the way these PDTs work, we don't need to have we don't have to do any target inspection, but we can if we want to. The opposite of from minima is to maxima. It spits out the largest value the PDT can represent since the largest. So, for example, C-long on Linux would be long. That means that since we know the largest a C-long can be is long, any value within a C-long can safely be pushed into a long and returned to Linux. So that's why this to maxima is a safe value. And you can see that these two are generic by instead of taking a target that's polymorph or using generics and as a subtype of target, we just take target and introspect on it. So finally, with regards to the pattern matching, everything I've discussed here actually enables us to do something like C's if-def pattern, except it's completely type safe. The compiler checks the code within these sections, and you're also able to do multiple platforms at once very easily. So for example, within this section, we've checked that target is either Linux x64 or Mac x64. So since we're using a case given here within this scope, we have access to information that C-long is a long, and then we're able to instantiate it with a long value inside of this scope. Meanwhile, inside this scope, we know that C-long is equivalent to an int, and we instantiate it with an int value. And if we pass in the wrong data or wrong types, we get compile time errors on any of these fields, as opposed to if-def, where errors in your code that is not chosen during an if-def just doesn't compile, and the error is leaked until you actually compile on the target platform. So just a quick summary, this is how everything works together. Here I'm defining just a type Sifu that I've just put together at random, and we do the match type here, and then just do the derivation of the mapping and the numeric. And this type now is able to do instantiation, can do unspecific or generic instantiation from unspecific, which takes int or long and returns some Sifu if the value matches the current platform. If, for example, if we were instantiating C-long and we passed in 5L and we're running on Linux, it would return some. But if we were running on Windows, it would return them. We also have access to from minima here since we did integral mapping. And the minima for Sifu is short. So that's a safe instantiation to go from 5 short to Sifu, and we have a free Sifu there. We can also inspect the platform to determine what we're running on and use much more platform-specific code to do instantiation. So here I'm using the apply instantiator, and this takes a short, this takes an int. Here you can use the generic unwrap to maxima, and that will return an int. The largest value for Sifu is an int, so unwrapping into int is a safe operation without inspecting the target. And finally, we can use the specific unwrap to get a type into a short this way, because this unwrap actually returns short, this unwrap returns int based on the platform. And finally, we can also just do math on these types very easily. Here we can do B plus C because of PDT numeric exists for C-long, and B and C were defined as regular Sifu, or defined for Sifu, and Sifu, B and C are proper Sifu, not options. And we can also mix and match these types by doing more platform-specific code. Here, I check if we're on Windows x64, and if we are, we execute this code where I unwrap the C-long here, F, and the C-long, or the Sifu here, F, and the C-long here, G. So on Windows, F unwraps to int, and G unwraps to int, allowing them to be added together, and then we can wrap them back into a Sifu, because Sifu takes int on this platform, getting back a Sifu.